you very much, Marcus, for this kind introduction, ladies and gentlemen. It's my pleasure to talk to you about the project HEPP this morning. I'll try to do my best to share the next 20 minutes with Sandra without overdoing the time. I'd like to walk you through the following points. Who is HSR and IET, for those who don't know who we are? Give you a quick introduction, really very quick, to power-to-gas and power-to-methane technology. I think it was introduced already, but I'd like to highlight a couple of details from it. Introduce you to two projects, Pentagon and the HEPP project, actually, and outline to you the key features of the demonstration plant we are building here at HSR. I would like to conclude my presentation with a short overview of the status and outlook of the project. Without further ado, HSR, the campus which you are here, is really the best campus in Switzerland, the most beautiful, I would say, is one of 7 Swiss universities of applied sciences. And we have, besides teaching of about 1,600 students, we have also an applied R&D area with 16 institutes and about 220 staff. The IET, Institute of Energy Technology, where we work, is one of these institutes, and we have about 40 staff working in the 6 areas you see in this slide. One of them is the power-to-gas area, where we have the 12 staff you see here, fully dedicated to R&D activities in the power-to-gas area under the leadership of Professor Friedl. Now, what is power-to-gas? Oh, sorry, excuse me. How did we actually started working in power-to-gas at IET? Well, the project you see outlined in this slide here was the first activity we developed there. We brought to Switzerland the first power-to-methane plant to demonstrate the technology of making renewable mobility from air, water, and sun. The small installation was here for about 2 years, and we could showcase the technology to about 1,000 visitors that came to us during the 2 years project lifespan. But what is power-to-methane, and why are we focusing on power-to-methane for mobility at HSR? I think that the basic of the technology has been introduced. We take power, we split water into hydrogen and oxygen with electrolysis. We store the hydrogen. This part of the chain is usually referred to as power-to-hydrogen. The hydrogen can be sent to direct use. We've seen that before in Tom Cobbler's presentation. But it can also be sent to the natural gas grid. Today, there's a limitation of about 2%. So an alternative would be to convert this hydrogen to methane via methanation reaction. For that, as we saw before, a CO2 source, such as biogas from a wastewater treatment plant, or CO2 from a combustion plant, or from the atmosphere, needs to be used. The reaction yields methane and water, but also some heat. That's important to keep in mind. That chain is usually referred to as power-to-methane. Now, we at HSR focus on the application, from the gas grid, the methane can be sent to seasonal storages. It is true that in Switzerland these storages are limited in capacity, but in the neighboring countries there's a large capacity to store this methane for a seasonal purpose. We at HSR look at the further chain, which is taking this methane to a gas station and using it into transport and mobility applications. Why do we do that? First, of course, the required distribution and infrastructure for the use of methane exists today, and the technology for its application, methane-powered cars, exists as well. The greenhouse gas emissions from the synthetic methane are lower than the emissions from the fossil fuel methane if we use a renewable power source. Yes, it is true. The production cost of synthetic methane is larger than the extraction and distribution cost of the fossil methane. But, as we saw before, under optimal conditions, the production and cost of this synthetic natural gas is lower than the current price at the gas stations. And we conducted a study that shows that we have production costs in the range of 12 to 19 Swiss francs cents per kilowatt hour, as opposed to biogas prices of 14 to about 16 Swiss francs cents per kilowatt hours. I invite you to browse to the study, which you will find in this link later in the presentation. Let me introduce you now to the Pentagon project. This is an EU-funded research initiative in which we, as HSR, are tasked with developing the link between the gas and the electricity networks with a high-efficiency system, which is described in this screen here. Basically, what we have in the power-to-methane plant that we're building here is a conventional electrolyzer producing the hydrogen to then be mixed with CO2 and sent to a methanation in a fixed bed reaction. As I mentioned before, a lot of heat is generated here. About 20% of the input here is available as heat here. What is important in our setup is that we will try to integrate, or we will integrate, a so-called solid oxide electrolysis cell, which was mentioned before already. This is a high-temperature system that requires steam for its function. Now, the interesting thing is that we use the available heat on this part here through a heat management system to generate the steam to feed the SOE. And this should bring us to about 70% efficiency AC to CH4 high heating value for large installations. We will be able to compare the PEM and the SOE routes directly. We will showcase a demonstration of the integration of this SOE, the heat management, and the methanation reactor. We'll have minimal infrastructure in this plant, and we'll operate this at a small scale with about 10 kilowatts power. It will be a data source for the Pentagon project, which is concerned, I heard a question before about software and integration of large systems, and actually designing a system to integrate all of this into an eco-district. And as said, our goal, our main goal, is to demonstrate an efficiency rise with this technology. Let me now introduce you to the HEPP project, which takes this concept into an industrial environment. We've taken the, let's say, core technology that we are designing or trying to build in Pentagon, and we actually try to integrate it with further industrial technologies, such as a PV installation as a source of power for our setup, CO2s from different sources, such as CO2 from the atmosphere or from a wastewater treatment plant, a state-of-the-art gas treatment plant here, gas analysis of a new design to simplify and lower the cost of operation of this system, methanation in different systems, new catalyst systems, such as sulfur-resistant system that is essential if you want to use the biogas as a source, and a sorption-enhanced methanation system that yields directly a pure product, doing away with the need for gas treatment. But also we'll have a fueling station, and we'll have the gas injection into the grid. And last but not least, we have a car to demonstrate the whole chain. I know this slide is even busier than the one before, but let me walk you through the details of this installation, starting down here with the water purification system, which takes tap water and prepares high purity water for the PEM electrolyzer up here. With this PEM electrolyzer, we generate hydrogen at about maximum 2 normal cubic meters per hour, 30 bar, and we put it into a low storage of between 5 and 12 bar. The same water can be sent to a preheating system here, and then to a steam generator that produces the steam for the solid oxide electrolyzer. The solid oxide electrolyzer works at atmospheric pressure, producing a hydrogen that is dry and stored in an intermediate storage vessel. Then it's sent to a compressor and brought to about the same pressure of the previously mentioned storage here. Our hydrogen is sent to a mixing and dosing station here, where we mix it with a part of the CO2 for the reaction, and we send it to a preheating and then to a fixed bed methanation reactor. This reactor has the possibility of adding a part of the CO2 as a means to control its temperature and temperature distribution. The reactor itself is a double mantle apparatus, which will be cooling with a thermal oil system, which extracts the heat from here and brings it over to the steam generator down there. Our product gases come then here to feed to preheat the feed, excuse me. The cool down gases then are used to preheat the demineralized water for the steam generator, and are finally condensed in the last step before we take the, let's say, produced methane and CO2 not converted and hydrogen to a membrane separation station. We'll then have the pure product gas coming here, and the unconverted gases are going to be sent to a compressor, a small storage, and then back into the reaction loop. Some key features that you see here: a maximum hydrogen feed of about 5 cubic meters per hour, CO2 3.5 normal cubic meters, and we expect a maximum production rate below 1.2 normal cubic meters per hour of methane. The installed powers: the PEM electrolyzer is a small unit with about 4.6 kilowatts, and the SOE will have maximum 10 kilowatts installed. Reaction conditions between 5 and 9 bar G and 250 to 300 degrees Celsius. As CO2 sources, of course, we'll start with commercial CO2 from bottles, but as I mentioned, we already have the biogas from a nearby wastewater treatment plant as a CO2 source, as well as air via Climeworks collector. I'd like to stress the point that we'll do our heat management with thermal oil, which is essential to the concept we're designing here. I'm not going too much detail here because you'll have the opportunity of actually visiting this installation. We are in the final phases of building it. Let me just say that we have the installation placed into a double container here, where you have the different process units around the main process unit, which you see highlighted here. There you see our reactor, our compressors, some vessels, the heat management system, and so on. I'll be glad to show you further details as we are then in the plant later on today. Where do we stand today? This picture is a recent image of the station in the inauguration. It was on the 4th of October this year. We've done the process engineering. We have all the components we need. The mechanical erection is pretty much complete. We tested the membrane module and the steam generator, and we did find out that some redesign is required, especially for the steam generator. The SOE module is being assembled by our partner EPFL, and we expect its delivery in January next year. We have the conventional catalyst already on site, and we will test some novel catalysts under pressure soon. Permitting is ongoing. We have already obtained a building permit and the gas use permit as well. We are in the phase of actually concluding our automation and electrical engineering, and we expect commissioning of this installation in January 2019. With this image of our partners, I'd like to conclude my part and invite my colleague Sandra Möbels for the next part of the presentation. Thank you.